You have no video evidence of this. Okay, so I am recording. We talked about this. We got to this slide. Small signal. We looked at those 4 transistor, single transistor configurations, the common source, the common drain, the common gate, and the common source with source resistance. So you should be able to calculate Rn, Rout, and AV for any of those. And to add to that, there are 2 more configurations we looked at. We looked at the cascode and the common gate. For the cascode, AV is GMRO, positive. And for a diff amp, the gain is GMRO. So being able to calculate those output resistances is helpful also. And then we went through here, we looked at the cascode, we looked at some current steering things, and we'll talk about those. And we looked at the MOS amplifier. It's really important. It's when people are building an amplifier inside an integrated circuit and they aren't building it to the point that they're selling it as an analog device, they're going to build a MOSFET differential pair. And they just add on to that and use different types of transistors if they're actually building these and selling them for like op amps and things like that. So this is really important. And these multi-stage amplifiers, and we will talk about that. One thing you really need to keep your good head on your shoulders when you're taking this exam. Stop and think. Really important. What do you know? Write down on the schematic everything that's given. Think about the resistors. Where do I know I'm only missing one variable? Where can I apply Ohm's law? And go ahead and apply it because it may help you. There's a couple of problems on here that there are at least half the points on the problem are things that are obvious if you do this. And then there may be some more subtle things later on to get full credit for the problem. But stop and think about this. If I know 2 of the currents going into a node and I don't know the third, I do know the third. KCL works. Be able to find REQs, be able to use voltage dividers. This is basic, and it will get you at least half credit on most of the problems, even if you're stuck. Most important thing to remember. MOSFET basics, 2 problems on the exam, and yet all the problems. Can you look at a device and given in looking using a symbol that looks sort of like this, tell what is the gate, the drain, the source, and the body, figure out where the current flows, and be able to identify what operating region it's in. Go back and get some practice with that on the homeworks or the old exams or the practice final. We did the layout. You should be able to identify a transistor now. A transistor gate is defined as active, poly over active. So this is my poly region. Oh, this is not going to show up at all. My poly region this is the width of the transistor. And this dimension right here, we really got to change colors now. Yellow. This is going to be the length. And this is a PMOS because it's bigger. And it's also in a N-well. And I don't know why I can't get rid of that screen, but this is an N+ diffusion. Poly over active defines my transistor. So this is the length of the NMOS transistor, Ln, and this is its width. I think this showed up on exam 1. And we've done enough layout now that you guys should be able to identify that pretty easily. Okay, remember, on the front page of the exam, I have Kn prime. I'm never going to have to do that calculation. It's written on the front page. I may have to do this one. The Kn of the transistor equals the Kn prime, which is on the front page, times W over L, if you know it. You know L, it's 0.13 micrometers. It's written on the front Yes, yeah. That's not, yeah, we did that in semiconductor physics in 280. What we got here, we've got the basic transistor. I have a constant voltage on the gate, so I'm only going to get one curve here. It is bigger than, VGS is bigger than VT. I'm going to get a curve like this. I get less resistance, and then I go up and it looks like a constant current source in saturation. As I increase VD, this channel starts to pinch off earlier because I start back biasing this junction right here. So what happens is the current is actually going to increase slightly because I'm increasing the resistance of that channel. That's where you get the 1 plus lambda or VDS thingy from. Know how to tell what operating region it's in and be able to identify the gate, drain, and source. I think this is like problem 1 on the final exam. Go back and look at your old exams, look at the old homework problems. This is the easy points. And if the grades on the exam are low, I tend to just like throw and do what I did on exam 2 in here, is just give everybody 10 points or something like that to make the average come up to a reasonable value. So get as many points as you can. It's not an easy final. Tyler Lee said this was the hardest exam he's ever taken before in his life. When we're calculating drain current, first thing you need to know is what region is it operating in? What about the body effect? If you're taking into account the body effect, oh, I'm going to have to change colors again. Go back to pink. The body effect is going to affect this number right here. So the first thing you would have to do is calculate what VTN is based upon the VT0 on the front page. This will be a function of VT0. So calculate that if you know VBS. If not, you can use the VTN on the front page and plug it in here. If it's in saturation region, I want to add this term in. That's the only place the 1 plus lambda VTS gets added into that equation. In triode, you can just go right here. Again, you have to pay attention to what the VT is.
Wait, Julie, why does it get added, the 1 plus lambda VDS?
It's what that output resistance is, it's the channel length shortens as you go further and further into saturation, and that increases the current. But that only happens in saturation. It doesn't happen in triode.
Why does the channel get shorter? I thought the channel was constant.
It gets effectively shorter because you actually get like a shorted, you get like a punch through on the drain to source side as that drain to source voltage goes up, and you get an effective shorter channel length, so the resistance of that channel goes down.
Because the drain is theoretically growing in size because there's so many electrons being emitted.
Right, there's so many electrons in that reverse bias region that it actually goes in there. Okay, so this is an effect that only occurs in saturation region. Never multiply the triode current by 1 plus lambda VDS. There's some practice problems on here. I suggest you, I'm not going to have enough time to go through them, but they're in the final exam solutions. This is a good practice for problem number 1 on the final exam. So make sure you understand this enough to get through it and have enough stuff on your note sheet that you can get through it. Yeah, and then we just talked about that. This only affects whatchamacallit in saturation. Output resistance. Now we learned when we did our amplifiers that output resistance is really important because it's in the basic model of the amplifier. It will determine whether that amplifier will work when it's hooked up to another unnamed amplifier that we will figure out later. So calculating RO, it ends up in the basic model of the transistor. It's just 1 over lambda ID. It should come out to be a couple hundred k ohms, 100 to maybe 400 k ohms for reasonable devices. We don't have to include that in the saturation current because this is just modeling that. These are equivalent. Don't do it twice. Okay. Mistakes I see on the exams. Okay. Now I said before that body bias is always important. It's going to end up, if we look at this equation, if VSB equals 0, this would be 2 phi f minus the square root of 2 phi f. That everything in there would be 0 if VSB is 0. So if VSB is 0, our threshold voltage equals the threshold voltage on the front page. If VSB is known and it's something other than 0, you're going to be expected to use that equation. Gamma is written on the front page. You don't have to do that calculation. Okay. I'm trying to give you as much stuff as I can to get you through this. And I want to see people pass. Digital MOS. Okay, so at least one problem. Do I have the final exam? Yeah, I did the final exam. I at least got that done this week. Okay, let's read the final exam to you. Yeah, I've already talked about problem number 1, calculate the currents. Problem number 2 is something from the practice final. Problem number 3 is calculating a DC operating point for a transistor circuit with some resistors and other devices in there. Given enough known stuff that you can calculate that. Remember Ohm's law. Problem number 4, you're drawing standard CMOS circuit from a function, and you're drawing another type of logic, pass transistor or dynamic logic from that same function. And tell me which one's better and why, and what parameters they're better with. Problem number 5 is the problem from hell. I'm just sorry about this. I don't know how to describe this. Go back and remember V equals IR, KCL, KVL. It's not as hard as it looks. You are going to have to calculate GM and RO. You are going to have to calculate those input resistances and output resistances, and we'll talk about that a little bit later. Oh yeah, and this problem is just 2 pages long. I'm sorry. I apologize for that one in advance. This is the reason why I have to have extra points on here. Okay, so we want to go back to this digital logic. I told you there was going to be, you have to do a digital logic circuit from a function on this exam. So the trick to doing this is NMOS. If I want to draw an OR, I put 2 transistors in parallel. And if I want to draw an AND, I put 2 transistors in series. Remember, this whole structure is inherently inverting. So I'm going to put a bar over the whole function at the end. And that will kind of get you there. We'll do one in a minute. PMOS is inverted. So if I want an AND, I have to put things in parallel. And if I want to put an OR, I put things in series. That comes about naturally in something I could do in about 10 minutes if I say that, well, it takes a negative voltage to turn these on, or it takes a positive voltage to turn the NMOS on. It becomes like the PMOS are the negative logic of the MOSFET world. Yet another reason why I like the NMOS better. Okay, so if I want to actually build a standard CMOS circuit, CMOS is not a type of transistor. It is complementary metal oxide semiconductor. It means I have both PMOS and NMOS in the same circuit. I need the pull down network to pull my signal low to ground when I want it to be low, and I need the pull up network to pull it to VDD when I want it to be high. Needless to say, the whole circuit does not work if VDD and ground are not connected. So if you leave the ground or the VDD off the circuit, I just automatically take a point off, just because, and it's a free point otherwise, if you can just remember to do that. Circuits don't work without power. So if I've got this one right here, I've got A and B are in parallel. So that's an NMOS. Parallel is OR. That's in series, that parallel combination is in series with C, and I put a bar over the top. Not too hard to figure that out. And this is like one of the standard interview questions in the semiconductor industry. Can you draw an NMOS, can you draw a standard CMOS NAND gate or an AND gate or something like that? Okay, gate oxide capacitance, we talked about this a lot. Just know that the capacitance varies in voltage, and you don't even need to know that for the final. You need to know very little about capacitance for the final. We've talked about these 3 different MOS structures. Now I care about this because when we get into memories and when you get into VLSI design, a lot of times this would be the ideal thing. And this is what I'm going to use inside a processor all the time because it's reliable, it's fairly compact, not very high power, performance is good. This is my go-to if I don't have any compelling reason not to use it. When you get inside something like a memories chip, there's a lot of drivers that have to fit in like 2 micron, tiny little 2 micrometer space, and I got to put the whole driver in there. Then I'm going to want to compact my logic down, and I'll use things like pass transistor logic. And the keys for pass transistor logic are whatever's on the drain and whatever's on the gate get ANDed together here. So this would be AC. I won't even talk about that one. This would be B, C naught. And those get wire ORed together. You just tie the outputs together to wire them. Very compact, loses a threshold voltage unless you go to this cousin of pass transistor called transmission gate here. But I can put in a really small space. So when space is at a premium, I'm going to do something like this. If whatchamacallit, another alternative I can get a little bit more reliable, this is only good like for half a clock cycle, is I use this dynamic logic and I can get rid of most of the PMOS network. So this is another way to do it. So these are the 3 basic types of logic people have developed. And what I see inside a memories chip is there's circuitry that's a hybrid of all of this, depending upon what they need to get the performance and the size that they have. And when we go to memories, we'll look at circuits like that and break it down and say, okay, this is an inverter, this is an OR gate, this is how this circuit works. And then we talk about physics a lot. And then we talk about signal integrity too, because it's like the most important thing in the world. So pass transistor, I told you that you're either getting, you're getting a standard CMOS problem on here. You're getting either a pass transistor or a dynamic logic problem also. I want you to study both of those. A single transistor can implement the AND function. What's on the drain and what's on the gate gets ANDed together, AC. It's not inverting. There's no bar on this. If I want to OR something, I just tie the 2 outputs together. It's called a wired OR. So can you draw circuits like this, and can you, can you analyze circuits like that? So here is an analysis problem. So this one right here is, this is an and, so this is BC. This is an and, so this is B naught. BB is B, B little b is B naught. B naught, B bar. ANDed with 1, so this is just B bar. I OR those together. I have B bar or BC. And if you remember Boolean logic or not, this actually reduces to B bar or C. I AND that with A. It's like, this is like De Morgan's theorem. I mean, it's not like De Morgan's theorem, but it's one of them that actually gets used. Down here, I have C naught, A naught, C naught. And that gets ANDed with A, the rest of the stuff. So the whole function would look like A naught, C naught, or A, B naught, or A, C. I think that's consensus or something like that, but I don't remember that. If you get it reduced down to this level, I'd probably give you full credit. If you miss this part, that reduction, I'd probably take a point or two off.
You were right. That's consensus. And then I think before that is De Morgan. It's like an elimination.
I know it's not. I know it's not De Morgan's theorem, but it is. It's one of those theorems like De Morgan's theorem that always gets used. I didn't mean to say it was De Morgan's theorem. De Morgan's theorem is like break the bar and change the sign.
It's elimination because it has the complement of 1.
Yeah, the way I tell people to remember this when I teach 110. Okay, so B naught or BC. If B naught is true, this term will be true, and that one's going to be false. If B is true, then this term is not true, and the whole function depends upon C. And so this is B naught or BC. There's another kind of like cousin of this that is like B naught or B naught C. That is just C. Or that's B naught or, wait, I don't remember. Okay. Let me think. You could factor out a B naught. Let me think through this. I started this. I'm going to have to finish it. B naught, and it would be 1 or C.
So it just be B naught.
So it would just, no, because 1 or C is always going to be 1. So that's B naught. Because that, yeah, and if you think, now I get it. If you look at this function, this can never be true unless B naught is true. And if B naught's true, it's still true.
And if B naught, yeah.
Okay. Digital wide 110. Okay, move back over to the other side of the room. So we want to draw some circuits here. I don't want to do the second one. That's too hard. We want to draw a pass transistor circuit. So we need B or C. I'm going to put buffer transistors in there just because I don't want to load down my, this may be somewhat extraneous. B or C. This is kind of a weird one to do. No, I would do it this way. B, C. I was actually building it. I would do this. And that's just because it would work better than anything else. And I want to AND that with A. This way I drew it, you don't load down your inputs, and all the current's actually coming off the power supplies. So here I've got C ANDed with 1 is C, B ANDed with 1 is B, and then so I put those two together, I have B or C. I AND that with A, I get A, B or C. Now there was something called the Shannon criteria, which meant if I would have to actually put things through here to make sure that it works correctly. Now let's say the A transistor is off. Then I would leave, this node would be floating. I don't want to leave floating nodes. So I'd put a transistor in here and tie this one to ground and make this A naught. If you at least get the basic function at some points, if you meet the Shannon criteria, you'll get all the points. And I just have to look at your circuit and see if it works. So some comparisons here. This is why standard CMOS, it's our go-to, higher noise margins, and it's faster. Past transistor logic, when I really need it, it's because it fits in a smaller area and it's lower power, so it's going to generate less heat. So when I really need it, I'm going to go that way. When I don't need the size constraint, standard CMOS is the way to go because it just performs so much better. Okay. Transmission gates, not on the exam. Same with this one. Dynamic logic. And this was the other one I said might be here. Which transistors are in the pull-down network? Right here. This works just like standard CMOS, pretty much. The function's going to be determined by what's in the pull-down network. So the function for this gate is going to be A or BC not. Just like it was a regular one. The difference here is I've gotten rid of the pull-up network. So in order to make the pull-up network, to actually charge this up to 1 when I want it to be 1, I turn this transistor on. And to turn this transistor on, I'm going to have phi low. So we could draw a timing diagram for this. So phi is, this is phi. When phi is low, this QP is on, and my output Y is going to be 1 no matter what I do. Now, when phi is high, this transistor goes off. This transistor down here turns on, and phi, whatever this right here is going to be determined by the value of A, B, and C. This will be a function of A, B, and C. So you have to figure out what the logic function is at that time to figure out whether it's on or off. Drawing the circuit, if you can draw a standard CMOS circuit, you just draw the NMOS network, add a transistor down here, and it's connected to phi, add a second transistor up here that's connected to phi naught. We'll talk about that more in 490 in the spring, if you take the class, if you choose to take the class. You don't have to choose to take the class. So if we want to draw the dynamic CMOS circuit to implement this function, it doesn't have a bar over the top, so we got to use De Morgan's theorem. Put a double bar over it. Y equals A bar or B bar or C bar, and it with D bar or E bar or F bar, and it with G bar bar. I hope you guys can see that. So we could draw the pull down network. It would look exactly like this, except we're going to put the, let me get a different color. This is driving me batty. Black might work. Does black work? So the pull down network is going to be, oh yeah, that's nice. A bar, B bar, C bar. You get another level of that. D bar, E bar, F bar, and that goes to ground, and I'm going to put G bar up here. And this is your pull down network. I put all the labels in there. A, B, C, D, why did I make such a big one? E, F. And then I would just have to add those two clocking transistors in there, and I would have the whole circuit. This would take, doing this in dynamic logic takes 1, 6, 6, 7, 9 transistors. Doing it in standard CMOS would take 14 transistors. So I can pack this in a much smaller area. Amplifiers. Yeah, there's one DC analysis problem on a MOSFET with like resistors and stuff on there. And do I have the key? I have it here. I'm getting tired. This is my second final review today. Amplifier. Oh boy, it's like the amplifier problem. Okay, sorry. Yeah, one's mostly just DC biasing of an amplifier. Can you figure that out? And one amplifier problem that's a real amplifier problem. And I'm just apologizing for that in advance. This can get you far. If you can identify whether it's a common source with source resistance, a common gate, or a common drain, I've got a chart here that tells me what the input resistance is. If it's a common gate, the input resistance is really hard to figure out. It's right there. What the voltage gain is and what the output resistance is. Now, if you have to look at a circuit and figure out what its output resistance is, and we did this a lot on exam 2, and yes, you'll have to do it on the final. If I'm looking into the gate of a transistor, I'm always going to see an infinite resistance. Looking into the drain, I see the output resistance of that transistor times 1 plus GM times whatever resistance is on the source, probably looking into another transistor or ground. And looking into the source, I get this formula here. So being able to figure out output resistances is a kind of a key skill. And I think I really nailed you on that on exam 2. Yeah, it got you a lot. For amplifiers, you can always assume it's in saturation. For hand calculations, you can kind of, if I'm not asking you to calculate current directly, you can ignore the channel length modulation and just go to this equation. If you know VG, you know ID, you know ID, you know VGS. Okay. This is the small signal transistor model. Did you have to use this anywhere on the exam? No, not directly. Did you have to calculate GM and RO? Yes. Different equations for RO. Note that they're not all the same lambda. You're given a lambda on the front page of the exam, and that lambda is in per volts, which is telling you you want to use this equation and not use these. GM, I'm frozen.
Oh, when you scribbled.
I scribbled, I did scribble. Okay, so GM. Notice that if you don't know KN, you can still calculate GM. And that will come up on the final exam. Someone will tell me, I don't know the size of this transistor, I can't calculate KN. How am I supposed to calculate GM? 2ID over V over voltage, although I will not tell you that during the final, and I will be back in a minute. So have all the versions of that GM formula. Who knows which one you're going to need. Slide 40.